So, good morning everyone. I'm Dr. Fasan from University of Trieste, and today I am presenting a preliminary work that has been done in the framework of a bilateral project financed by the Ministry of Foreign Affairs between the University of Trieste and the Institute of Geophysics and Astronomy of Egypt. So, in this work, so let's talk about the project. The project is about the religious complex in Cairo, which is an old cultural heritage site, UNESCO site, where in about 200 meters by 200 meters there are 7 different religions. It has been built above an ancient Babylon fortress, so it has some of the structures have more than 2,000 years. And the project is about evaluating the seismic risk and some, let's say, mitigation strategies to preserve the churches, the mosques, the synagogues that are inside the site. The problem is that the area is a moderate seismic risk area. That means that there are really few data about recorded earthquakes, so accelerogram, and also few data about historical earthquakes. But there are information telling us that some earthquakes up to magnitude 6.5 can happen near Cairo. So the objective of the project is, first of all, to assess the seismic risk and the seismic vulnerability of the complex. Then, based on this, propose some simple conservation techniques. So, let's say, to increase to reduce the vulnerability of the complex, and also to, let's say, inform the Minister of Antiquities of Egypt on techniques that he could apply also elsewhere to improve the vulnerability of the cultural heritage buildings. The main innovation about this project is the use of physics-based ground motion instead of GMPs to evaluate the seismic hazard. Why we do this? Because there is a lack of data in Egypt to reliably constrain the GMPs and also to have information about what could happen at the site. So the use of physics-based ground motion can be a tool that can be used alone or together with GMPs to gain more information about the hazard. So the methodology is to assess the hazard using physics-based ground motion. Based on this, we generate 3 components synthetic accelerogram that include actually source effects, path effects, and site effects. And then to use directly the seismograms, the accelerograms that we generated to run nonlinear time history analysis of the buildings. So it's an interdisciplinary approach that combines geoscience and structural engineering. And here you can see the workflow of the project. So it's basically assessing and evaluating the properties of the source, simulate the rupture process of the source, evaluating the properties of the medium that is interposed between the source and the site, so the structure, the soil structure, let's say, the crustal model, and also the site-specific model to include also site amplification and changes in the ground motions. Why do we use ground motion, why do we use physics-based ground motion simulations? Because what we want to look is at the impact of low probability, high consequence events. That is really important to evaluate the possible damage that could happen in a cultural heritage site, above all like this, that has some of the buildings have more than 2,000 years. So let's say, in principle, it's not possible to evaluate a seismic action for which the loss of the building can be acceptable. So an accurate estimation of the seismic hazard is needed, and also an accurate estimation of all the uncertainties that we know should be included in the hazard, at least to see what is the impact. So also the use of physics-based ground motion allows us to use those instead of GMPs in an area where they cannot be constrained really well because of the lack of data. So physics-based ground motion are based on geophysical and seismotectonic features of the region, and they basically defined by the position of the source, the magnitude, the distance from the site, and the faulting style. As I said, they consider all the main effects, so source, site, and path effects, and most of all, they can provide accelerograms that are useful to run structural analysis. Here we can see there is a table where we selected seismic sources that can affect Cairo, and we included also the uncertainty on the main parameters that we have to use to run simulations. And as we can see, of course, this depends on the site. If we do this in Italy, the uncertainty is way lower because we have more information about seismic regions, about seismogenic zones, and so on. In Cairo, the uncertainty is huge, so none of this data is actually true, but the truth is among them, let's say this. And so what we decided is that to include both epistemic and aleatory uncertainty, just running more scenarios, combining these parameters. So in this case, we concentrated just in one source, which is the one that where it was originated, the Cairo earthquake of 1992. So we selected just the maximum magnitude, even though we could do more, because it depends also on the period, on the distance. So for this preliminary work, we decided to use just the maximum. And what we varied was the depth, the dip, the strike, and the rake, so the main parameters of the faults. So all these 6 pictures represent actually the same fault, and it's a representation of the uncertainty that we have in its definition, because the position can be this or this, we don't know, or something in between. Here, we just moved the strike, the dip, and the rake at fixed ranges, for sure to evaluate all the variability due to the uncertainty and these parameters. We should use we should do more scenarios. These are just 24 scenarios to see what is the influence, but we should increase the numbers. So this is about epistemic uncertainty, so what we don't know actually very well about the source. This is about the aleatory uncertainty, so what actually it's random, so it's linked with the phenomena, which is random itself. So this is basically linked with the source, so how the source is going, how the rupture of the source is going to be. So what we want to do is to simulate the front rupture and the slip distribution, so the slip on the fault plane. And here are just 4 different representations of a rupture of the same fault. Okay, so what we do is we simulate the slip on the fault plane, the nucleation point, so the point where the rupture is going to start, and the evolution of the rupture front, so the velocity of the rupture and the main direction, let's say, of the rupture. In this approach, it's a kinematic approach that can allow us to also to include the effects of the activity in the accelerometers that we are going to simulate. So going to results, we did this for a lot of intensity measures. Here I'm showing you just PGA and spectral acceleration. And what we see here is the blocks in the pictures are just different rake angles. And the colors represent the variation of dip, strike, and rake. So basically, each vertical line represents the aleatory uncertainties of those scenarios, and each of the different scenarios represents the epistemic uncertainty. So we can see it like this. Also here I show north and the north-south component and the east-west component, but also the max rot D100 component, which is basically the resultant component, so the composition of the two components, a vector composition at the maximum. And as you can see, what we can see is that the components as recorded can have a really huge variability between the different scenarios. And this can be reduced using a bidirectional component. So for example, the max rot D100. Also, what we can see is that basically we cannot establish a trend. Okay? So there is actually, in this case at least, there is no possibility to find a worst case scenario, but the only thing that we have to do is to simulate everything and then look at the numbers that we get. The same thing is going to happen, for example, for spectral acceleration. So same consideration, no clear pattern is arising. This can be, actually this could be just the effect of this source, because the uncertainty that we have in this source was really huge. Mainly, probably for a source, for a fault in the Italian territory, this could be different, because the range of variation is really lower than this. And what we can still see is that it's better to use a bidirectional component instead of as recorded ground motion. So basically, what is the result of this preliminary? This is going to be actually the data that we are going to use to assess the hazard at the site, some of the data. And it is what I wanted to show you is just how important it is, above all for cultural heritage site, to include all the uncertainty, even though we have few information, but if we have a range to look at, we have to explore everything. So basically, the conclusion is that, of course, the variability of the seismic source is really significant and affects really significantly the ground motion that we record at a site. The epistemic and authority uncertainty should be rigorously integrated in the seismic hazard assessment, both deterministic and probabilistic, it doesn't make any difference. And physics-based approach, as the one that we used here, it's a tool that can allow us to do accurate seismic hazard assessment even in sites where we have not enough recorded data, let's say, for example, to constrain a reliable GMPs. And they can be also used side by side with GMPs to check the results, for example, to check the results. And above all, for sites like cultural heritage sites, it's really important to include uncertainties and to look at what could happen, just to have at least an idea of what can be expected in such an important site. And I'm done. I hope I was clear, and thank you.